Welcome back, students. Dear students, in this session, I am going to explain the topic Carnot Cycle. Let us see the Carnot Cycle, how it operates, and also we can see the expression for efficiency of the Carnot heat engine. Dear students, see in this diagram, this is Carnot's ideal heat engine. This one is Carnot cycle. In order to obtain continuous supply of work, the working substance is subjected to the following cycle of quasi-static operations known as Carnot cycle, or a heat engine operating in an ideal reversible cycle called a Carnot cycle between two reservoirs is the most efficient engine possible. Dear students, to describe the Carnot cycle, we shall assume that the working substance is an ideal gas contained in a cylinder with a frictionless movable piston as shown in the diagram here. The Carnot cycle consists of the four stroke. One is isothermal compression, second one is adiabatic compression, third one is isothermal expansion, fourth one is adiabatic expansion. Let us see these four stroke one by one by assuming this Carnot cycle, by referring this Carnot cycle here. First one is isothermal expansion. When the cylinder placed on the source, the gas acquires the temperature T1 of the source and it is allowed to quasi-static expansion as the gas undergoes expansion. As the gas expands, its temperature tends to fall. Heat passes into the cylinder through the conducting base which is in contact with the source. The gas undergoes slow isothermal expansion at the constant temperature T1. See here in this diagram, we have taken the ideal gas inside the cylinder which is fitted with frictionless piston. When it is kept on the source which is at high temperature T1, then the gas undergoes expansion, hence it undergoes a slow isothermal expansion at the constant temperature T1. The working substance during isothermal expansion, goes from the state A which is at T1 V1 T1 to the state B which is at P2 V2 T2 at a constant temperature T1 along AB. Hence the substance absorbs the quantity of heat Q1 from the source at a temperature T1 and does work, that is W1, let it be W1, work. Therefore, quantity of heat absorption is equal to Q1 equals work done W1, that is equal to P into dV. This is nothing but work done by the gas between the volumes V1 and V2. This is equal to area A, B, G, A, B, G, E, A. This area represents work done by the gas in the Carnot cycle. Let us see the second one, adiabatic expansion. Now the cylinder is removed from the source and is placed on the insulating stand. Just you refer the first diagram of first slide. Now cylinder is removed from the source and is placed on the insulating stand. Now the gas is allowed to undergo slow adiabatic expansion, doing external work at the expense of its internal energy until its temperature falls to T2 degree Kelvin, the same as that of the sink. The sink is also at a temperature T2. This operation is represented by the curve BC, starting from the state B to state C. In this process, there is no transfer of heat. The temperature of the substance falls to T2 and it does some external work that is given by the formula W2 equals P into dV, which is integrated between the limits V2 to V3, because B, the state B at the volume V2, C the volume V3. Hence the area B, C, H, G, B. This area represents the work done during adiabatic expansion. Adiabatic expansion. Here during this one, there is no transfer of heat takes place. Let us see the third one, isothermal compression. Now the cylinder is removed from the insulating stand. The cylinder is now removed from the insulating stand and is placed on the sink at the temperature T2. The piston is now very slowly moved towards so that the work done on the gas, work is done on the gas. When the piston pushed inside, then there is a work is done on the gas. The temperature tends to increase due to heat produced by compression. The heat developed passes to the sink and the temperature of the gas remains constant at temperature T2. Thus the gas undergoes isothermal compression at constant temperature T2 and gives up some heat to the sink. Here, when the cylinder is removed from the insulating stand and placed on the sink at T2, then work is done on the gas. Thus the gas undergoes isothermal compression at temperature T2 and gives up some heat to the sink. This operation is represented by the isothermal CD as shown in the Carnot cycle diagram. Along CD, starting from the state C, which is at P3 V3 and T3, to the state D, which is at T4 V4, the substance rejects heat Q2, quantity of heat Q2, to the sink at the temperature T2, and work is done on the substance is given by the formula. The quantity of rejection, heat rejection Q2 equals nothing but work done W3, that is equal to integration of P into dV between the limits V3 to V4. Hence the area C, H, F, D, C. C, H, F, D, C. This is the heat rejection, nothing but work done on the substance. Now you can see the fourth one, that is adiabatic compression, the fourth stroke. Now the cylinder is removed from the sink and again placed on the insulating stand. Just you remove the cylinder from the sink and again placed on the insulating stand. The piston is slowly moved towards so that the gas is adiabatically compressed and the temperature rises. The adiabatic compression is continued till the gas comes back to its original condition, that is state A, thus completing one full cycle from A to B, B to C, C to D, D to A. It completes one full cycle from A to B, that is isothermal expansion, B to C, adiabatic expansion, C to D, isothermal expansion, and D to A as adiabatic compression. Hence, it completes one cycle. This operation is represented by adiabatic dA, from D, which is at P4, V4, T4, to the final state, that is, which is at A, P1, V1, T1. In this process, the work is done on the substance and is given by the formula. The work done on the substance is W4, which is equal to integration of P into dV between the limits V4 to V1, and the area, this represents area, that is D, F, E, A, again D. D, F, E, A, D. This area represents work is done on the substance. Now, we shall discuss about expression for efficiency of the Carnot heat engine. Dear students, thermal efficiency of a heat engine is defined as the ratio of external work done to the heat absorbed by the working substance from the source. That is, efficiency equals, that is, ratio of work done to the quantity of heat absorbed, that is W upon Q1 is equal to work done, means quantity of heat absorbed minus quantity of heat rejection. The difference of these two, heat energy, gives work done, divided by the quantity of heat absorbed Q1. Therefore, efficiency eta equals, that is T1 minus T2 divided by T1 for ideal engine. Actually, in practice, the efficiency of the Carnot heat engine is given by the formula eta equals 1 minus T2 upon T1, T2 upon T1, or eta equals 1 minus Q2 upon Q1. Here it is by mistake written as gamma, it is not gamma, make it correction. This is T2 by T1 or 1 minus Q2 by Q1. For real heat engines, efficiency is lesser than equal to 1 minus Q2 by Q1. 1 minus Q2 by Q1. That's all. Dear students, from this session we can learn the 4-stroke nature of Carnot heat engine and also the expression for efficiency of heat engine. Thank you.